This video will help with your Newton's Law assignment. So you should have watched all the videos about Newton's first, second, and third laws. In your assignment, it seems kind of a morbid assignment. It's about car crashes and whiplash and breaking legs and things. But the thing you have to remember about inertia, remember the definition of inertia is the resistance to change motion. So for example, in car accidents, so this is resistance to change motion. So if your body is moving forward, it wants to continue moving forward until something stops it. And so your first question deals with the concept of whiplash. So imagine that your body is attached to the car. So you're wearing a nice seatbelt and your body and the car move as one, but your head is not attached directly to the car because the seatbelt's around your shoulders, not your head. That's why race car drivers often do sort of wear things keeping their head from flying around. Okay, so let's assume that you are going forwards. So your body and the car and everything is nicely going forward, and you're hit from the front, you're hit head on. Okay, so if a force is exerted to the left, this is the force of impact with another vehicle or a post or something. What's going to happen is your head's going to keep going. So this will essentially stop the car, but your head keeps going. And so your head ends up over here, and your head, your neck would then be strained tremendously, and your head would hit the windshield. So that would be for a head-on collision. Similarly, if you were just sitting, say, at a red light, and your head was merely at rest, and somebody hit you from this direction, so this was the force of impact, well, what would happen would be the car and your body would move over as a result of that impact, but your head would stay where it was. And that's when your head doesn't actually go backwards. It's just that the car and your body go forwards out from under you. And so this would then result in your neck being strained tremendously in this backward direction. Okay, so that's Newton's first law. Now, Newton's second law, which is that F net is m times a. We know all about F net. We know how to add forces up to get net forces. And so now we see that these net forces cause acceleration. And so if your body is subject to a bunch of forces given acceleration, you can relate the two quantities. And so you can see here that big accelerations result in big forces because they're directly proportional. So if this is big, then this is also big. So once again, thinking about car crashes, if you're moving around in a car and you're moving at some high velocity VI, and then you hit a brick wall and the car gets all smashed up and a mess here, VF would be 0. Okay, now the acceleration, we've got two equations for acceleration. We've got the VF minus VI divided by T, or we have the acceleration equation where VF squared minus VI squared over 2 delta X. Now, if you're going to crash and come to rest, VF is 0. Okay, so we've got two types of accelerations here. That's the same acceleration, it's just depending on what values you're told. Either you use that equation or you use this equation. Now, it's undesirable to have a huge acceleration because that results in a huge force, which results in a lot of damage. So how do we reduce the acceleration? We want to reduce this. Reduce acceleration to reduce net force. Well, we can't do anything about your initial speed. That's your initial speed before the accident. The thing you want to do is you can change these values, the time or so this is the time to stop. So T is the time to stop, and delta X is the distance over which you stop. And cars are equipped with things to help increase these values. So you want to increase these things. So you want to increase T or delta X because it's on the bottom of the equation. If you make the number on the bottom bigger, you make the number on top smaller. So you want to increase the time or delta X to stop to reduce force, reduce net force. And so cars have things built into them that let you do this. The first is an airbag. So the purpose of the airbag, rather than your body coming to rest very quickly by hitting the windshield, just with your body, the airbag brings your body to rest in a much longer time because the airbag then slows down your time to come to rest. It also tends to increase the distance over, so it's got both these effects. So airbags do this. The fact that the crumpling of your trunk in front of your car, so it's kind of like a spring. So this would be the stopping distance. So crumbling trunk do this as well. Crumbling trunk do this. Okay, they would, as the trunk of the car takes the impact and crumbles up, then both the time and the distance over which you stop is increased. And so that decreases your acceleration, which decreases the force. Okay, so you have a couple of problems that use those concepts. There is a problem about jumping where the forces are given. I've done a video of that separately. It's a bit of a rough video. It was done last year on an old clanky computer. But you can have a look at that video, and I'd recommend that you then write out that whole question about the girl jumping on the force plate. But just a little bit more about jumping. So there are two stages to jumping. First is when you're in contact with the ground. So when your feet are in contact with the ground, so if you want to jump up high, say you're doing a vertical jump test, you bend your knees, you start at rest. So you bring your body down, now you're in a crouch, you're at rest. And then you push off the floor as hard as you can with your legs until you're still touching the floor though. So you straighten out your legs until you reach your takeoff speed. And so VF would be your takeoff speed. Now during that process, you are not in free fall. You are under the influence of two forces, not just gravity, but the normal force as well as gravity. And so the free body diagram during this push off the floor would be, so here's your body. You have the normal force. This is force of floor, and that is what is actually propelling you up. The harder you push on the floor pushes back. So this is force of floor on you. And then of course you always have gravity. You can't change that. And so your net force, remember it's the net force that results in acceleration. So F net, and people often forget the force of gravity. They think the only force on you is the floor, but your net force is up minus down. So it's Fn minus Fg. And that is equal to m times a. And so the normal force on your body that you create by pushing as hard as you can, now you don't have to do anything. If you just stand there, it would equal your weight. But if you want it to be bigger, you're going to have to push off the floor, is equal to Fg plus ma. Or if I write Fg as mg plus ma, is equal to mg plus a. And this is kind of a handy little equation here. So Fn is equal to mg plus a. Remember, this is always positive. And it equals 9.8 newtons per kilogram. This is not an acceleration. This is just the strength of the gravitational field used to get the force of gravity. That's always positive. This is your acceleration. Acceleration. And that comes from the VF minus VI over T, or VF squared minus VI squared over 2 delta X. It depends what you're given. So, for example, if let's say, and VI is 0 for this jumping. Okay, so those equations are always true. So assume VI equals 0. This is you in a crouch, ready to push off. And then let's say that you leave the ground at 5 meters per second. That's pretty high. Okay, so this is velocity. You leave the ground, but on the way up, after you've pushed off and you've become a free falling object. So this is velocity. You leave the ground with. And that's positive because you're jumping up. And then let's say we're also given that at the time that it takes you to go from a crouch to take off, it's pretty quick. Let's say it's half a second, 0.5 seconds. The question is, what's the normal force on your body? So if you were jumping off a bathroom scale, what would the bathroom scale read? So what is normal force on body? And this could be pretty significant force. So let's get our acceleration. It's VF minus VI over T. So VF is 5 minus 0 over half a second. This is plus 10 meters per second squared. That's independent of the 9.8. This is just from you pushing off. And so the normal force, if we use that equation, it's very handy. And that's a positive acceleration because your Fn is up. Mg plus a. Now I'd have to know what your mass is. Whatever. Say it's, I don't know, 60 kilograms or something. And this would be 9.8 newtons per kilogram plus 10 meters per second squared. So this is almost double your weight. So the force, the scale, you could actually get a bathroom scale to read double your weight if you're able to push off to a takeoff speed of 5 meters per second in half a second. Okay, so that's jumping. Now, similarly, landing from free fall. So if you fall off a desk or something and you land straight-legged, it's pretty severe force because landing straight-legged. So let's compare straight-legged straight leg landing to bending your knees. So maybe you're just not consciously able to bend your knees and you sort of accidentally just land straight-legged because it happens so fast. Let's see how much more force that's going to exert through your leg bones, bone on bone, and see if that's going to break your leg. Okay, so what the difference is, so you fall off of something, you're falling through the air, you're still in free fall here. And so you have an initial velocity. And it depends from what height you fall. I think we worked out that if you fall from a 3-meter roof, we got a number like negative 7.67 or something. So let's just say it's not quite that bad. Let's say you're falling at negative 5 meters per second. And then you're going to come to rest. You're going to stop. You've got two choices. You're either going to come to rest over an incredibly short distance, which is basically just your heel pad absorbing all that momentum that you have. So it'd be very short distance. So if it's just the heel pad, then the delta x, like from here to here, the distance over which you stop would be tiny. Let's say it's only, I don't know, 5 centimeters. It wouldn't even be that much. But you might, all your joints kind of might squish together a little bit. So let's say the distance that it takes to stop you is 5 centimeters. Now remember, this is your center of mass that has to stop. This, because when you're in free fall, you're basically just one big blob at your center of mass. Okay, but think about if you bend your knees when you land. So if you come down and you bend your knees, now as you come to rest, much bigger distance. So let's say now it takes like 0.6 meters because your center of mass goes from wherever it is just before you land way down. So there's a much bigger distance. Okay, so let's calculate the accelerations in these two cases. VF is 0 in both cases, you stop. And the interesting thing, which way is this acceleration and which way are these displacements? Well, if you're falling down, this displacement would actually be a negative number. And so would this one. And this is because you're moving down as you come to rest. So we better put that negative in there. And a negative. Okay. VI is negative because you're traveling down before you hit the ground. So you're moving down. Okay, and VF is 0. So let's see what your acceleration is in these two cases. So acceleration, we're going to use the VF squared minus VI squared over 2 delta x. So this would be 0 minus VI squared over 2 delta x. Okay, so for straight legs, where delta x is negative, what did I say, 5 centimeters, so it's 0.05 meters. We got that A is negative. Now the negative 5 gets squared in there, but the negative out here stays. This turns out to be a positive acceleration. The net force on you is up in order to stop you. So let's see, 25. Well, this is a pretty big number. Whoa, this is 250. That's pretty extreme. 250 meters per second squared. But now let's do bent legs. That would do an awful lot of damage, where delta x is negative 0.6 meters. So then you really bend your legs. We get an acceleration of negative, same initial velocity. Now it's 0.6, so this is significantly smaller. Or you make the number on the bottom bigger, you make the number on top smaller. So this is only 21. Still pretty big though. So it's still pretty tough on your body to bring yourself to rest, having fallen, so your speed just before you hit is 5 meters per second. Okay, so what is the normal force? Remember, it's the normal force that's going to do the damage to you, because that's going to be the pressure through your body. So remember, the normal force is mg plus a. So it's the same equation. So it's m, it would be 9.8 plus 250, huge. This would be straight-legged, or it would be, that would probably break a bathroom scale if you jumped onto a bathroom scale and had the bathroom scale read that kind of number. Or 9 point. Now remember, there's still positive. Both accelerations are positive, and this normal is positive because they're, if you're going to stop your body from going down, you better push on you up. And this is bent legs. Okay, so pretty big significant difference there. Okay, that should take you through all of your assignment questions for that Newton's Law assignment.